In this video, we will look at a real life problem based on the two-factor factorial design, the battery life experiment. So, in the problem, the researchers were interested in studying the effect of temperature and the material type used in the battery plate. These two factors, the researchers were interested in studying the effect of these two factors on the battery life. So they suspected that their battery design, uh, the life of their battery design varies depending on the atmospheric temperatures, and they wanted to see which material type can be more robust. So they chose three temperature levels: 15 degree Fahrenheit, 70 degree Fahrenheit, and 125 degree Fahrenheit for their experimentation. And they chose three material types for the battery plate. So if we designate material type as A and temperature as B, so one thing you will notice that the temperature is a quantitative variable. It is basically the numbers, right? 15 degree Fahrenheit, 60 degree Fahrenheit, and so on and so forth. And material type is a qualitative variable uh, because there are different types of material. They are not numbers. So the couple of things that the researchers are interested to know is: first question, what effects do material type and temperature have on the life of the battery? That's the first question. Second question is more important: is there a choice of material that would give long life regardless of temperature, a robust product? So this is like a two-dimensional problem. You may get a material type that gives you that gives the highest battery life, let's say at 70 degree Fahrenheit, right? But that battery lives drop quickly uh, if the temperature changes to 15, drops down to 15 degree Fahrenheit, or temperature increases to 125 degree Fahrenheit. If battery life drops out significantly, then that is not a good material type, even though it gives you the best life at certain room temperature, for example 70 degree Fahrenheit. But it is not robust enough because that battery life drops significantly when the temperature changes. You would rather have a material type that gives a little less life, but it maintains its battery life across the range of temperatures, right? So absolute high value at one temperature versus the robust or the consistent battery life at various temperatures, that's the trade-off. Ideally we would like to have the best life and most consistent life across various temperature range. If we have such a material, that would be the best choice, right? Another thing you will note here in the table that so factor A, material type, has three levels. Factor B, temperature, has three levels. So we can perform three times three is a nine unique experiments we can perform, right? Like material type 1 and 15 degree Fahrenheit, material type 1 and 70 degree Fahrenheit, and so on and so forth. So they performed four experiments at each unique combination of material type and temperature. And in the table, what we have is actually the battery life measured in hours: 130 hours, 155 hours, and so on and so forth. So we have a 3 by 3 factorial design with four replicates, and a total number of experiments or total runs is basically 36. So here is a general representation of a two factorial design. We have a factor A versus factor B. Factor A can have A number of levels. Factor B can have up to B number of levels, and uh, N is the sample size. So we have N number of experiments for each unique combination. So that's a general representation. Uh, and these runs here, different experiments, they are performed uh, in completely randomized order. So uh, we can form a statistical effects model for this type of experiments or this type of experimental design. So any observation yijk, where I represents the ith level of factor A, J represents the jth level of factor B, and K represents the kth iteration in kth replicate out of the n replicates. So any observation like in this case here, this is y1, y111, y 112, y113, and so on and so forth. So any observation in the table yijk can be given by mu, some mean, right? If there is no variation, there is no effect of the material type, or there is no effect of the temperature, no interaction effect, or not even a standard noise, then every time we repeat the experiment, we should get exactly same battery life. But that is not the case. Every time we repeat the experiments, we get a different result. There is a variation, right? As you can see, there is a variation in numbers. We are getting different battery lives for each experiment. Even with the same combinations, we are getting different battery lives, right? So that variation can be divided based on the contribution of each of the factors. For example, there is a mean, right? No variation, plus tau sub I is the effect of factor A, material type, right? Plus beta sub j is effect of the temperature or effect of factor B, and tau beta is the effect of the interaction effect between factor A and factor B, material type and temperature in our case. And epsilon ijk is these are standard errors, right? All other factors that are not under consideration, but they may be there, so their effect is epsilon ijk. Those effects are independently and normally distributed with constant variance, where I varies from 1 to A, J varies from 1 to B, and K, sample size, varies from 1 to N. Now, this is called as effects model that can be represented in other forms such as means model or regression model, particularly for quantitative variables. Those can also be useful. So here is the breakdown of your total variability into different components. So sum square total is divided in sum square due to factor A, sum square due to factor B, sum square due to the interaction effect, plus sum square error. Now you will notice that the total variability, individual observation minus a grand total squared, is divided in, for example, sum square A. Sum square A, you will see basically it is the row averages minus the grand average squared. Then sum square B is basically column averages minus grand average squared, and uh, the interaction effect is basically the cell average minus the row average and the minus the column average. So cell average minus the uh, effects of uh, factor A and factor B, and the lastly, the sum square error is basically individual observation in one cell minus the cell average. So that's the error, because otherwise in one cell all observations should be same. If there was no error present, all observations within one cell should be the same values, but they are not. That's why this each value within the cell minus the cell average squared is the sum square E. Then we have degrees of freedom breakdown. Total degrees of freedom is A, B, N minus 1. Total number of experiments or total runs minus 1. Degrees of freedom for factor A. Factor A has small a levels. So A minus 1 is the degrees of freedom for factor A. Degrees of freedom for factor B is B minus 1. factor B has B labels, so B minus 1 is degrees of freedom. Degrees of freedom for interaction is basically the multiplication of degrees of freedom for factor A and degrees of freedom for factor B. A minus 1 times B minus 1. And sum square error is always AB times N minus 1. So basically N is the sample size. Within one cell of the table, there are N observations minus 1, that is for one cell, degrees of freedom for one cell, times there are A times B number of cells. So that's the degrees of freedom for error. So all these calculations can be summarized in a nice ANOVA table. So source of variation in our values, the different sources of variation, variation because of factor A, variation because of factor B, interaction effect, error, and the total variation. So we have sum of squares column, we have degrees of freedom column, then mean square is basically sum square divided by its degrees of freedom, right? SSA divided by A minus 1, and so on and so forth. And F values is we compare basically the effect of the particular factor against the effect of the error. So mean square error divided by mean square error is the F value. Similarly, F value for factor B, mean square B divided by mean square error, and so on and so forth. Then you can compare these F values with the critical F values at alpha value of 0.05, or you can look at respective P value uh, to decide whether the effect of these various sources is a statistically significant or not. So this is a summary of all the calculations that you will need. Right, in the textbook we have uh, formulas for manually computing these values, and it gets very complicated. You will make mistakes in manual computing, so it's a good idea to at least practice couple of times using manual computing. But eventually the softwares like Jump, Design Expert, Minitab, uh, or any other advanced statistical software that can perform the computations easily for you. Here are the equations from the book for the manual calculations. And as I said, you need to practice it a couple of times to understand how to perform manual calculations. And here are the results of design of expert software. You will see that this particular table that design expert software outputs for you. uh, First, it shows the model sum of squares. Model means it combines the effect of factor A, B, and AB into one, which is called as model. So, as you can see, sum of squares is the total sum of squares for not total, for these three terms combined is the model. Degrees of freedom, we have for factor A, we have 2 degrees of freedom because we are using three different three plate types. So that is, going back to just show you again, we are using three different material types. So 3 minus 1 is 2, and we are using three different temperatures. So 3 minus 1 is 2 degrees of freedom for material type and temperature, right? So here, so those 2 degrees of freedom, 2 degrees of freedom, and then 2 times 2, 4 degrees of freedom interaction. If you add all of them, 8. That's the combined model degrees of freedom. So just looking at the first row, you can see that your p value is 0.0001, uh, which you compare with alpha value of 0.05. You see it is very small. It is very small. So we can say that the model is significant. At least one of the terms in the model has significant impact on the output. And now we have the breakdown of the model. Fact, material type, temperature and the interaction effect between the material type and temperature. So looks like material A is significant. Once again, it's less than p-value is less than 0.05. So material type has a significant uh, effect on the battery life. Temperature is highly significant because it's a very small p-value, and the interaction effect, though not as prominent as the main effects, but it is still statistically significant because this p-value is also less than 0.05. So that's how you basically make the conclusion. This is output from jump software. Jump software shows a little different way. It first analysis of variance only for the model, same ideas but presented in a different fashion, and then the model is broken down into material type, temperature, and the material type times temperature, which is the interaction effect. We have also residual plots shown in the jump output, life residual versus life predicted, and we want to see no pattern in those plots, right? We want to have this randomly distributed dots here. Then to check the assumptions on residuals, we can do the normality plot of residuals, and looks like the residuals or errors are, if you draw a line, they are basically perfectly aligned with the line. If you use a thick pencil test, if you put a thick pencil on this line, all these residuals will hide under the line. That means the normality assumption on residuals is satisfied. And what does that mean? In the statistical model here, the errors, the residuals, they should be normally and independently distributed with constant variance, right? So that's what we are checking, whether normality assumption, normally distributed, that assumption is violated or not. So looks like that assumption is good. The residuals are indeed normally distributed. And constant variance, we can see from this plot here, plot of residuals versus the expected predicted values. And we don't want, the thing we want to see is, we don't want to see any pattern. So we don't see any pattern, so that's looking good. We can also make residuals versus material type and residuals versus temperature plot. Once again, we want to see uh, no pattern in these plots. So these two plots can also be important to gain some additional insights into the behavior of residuals. And lastly, I want to talk about this plot here uh, to actually graphically show how the factors are affecting the battery life. So here we have, on x-axis we have temperature 15, 70, and 125 degree Fahrenheit, and on y-axis we have the life of the battery. And you will see that the different colors here, different color graphs, they show different plate materials, A1, A2, A3. So one thing is obvious from the graph is the battery life is dropping off as temperature increases. The battery life is dropping, right? We get the best battery life probably at 15 degree Fahrenheit, and as the temperature increases, the battery life drops. But more interesting things to see is how the battery life drops for different material types. So if you see, for example, material type A1, the black plot here, uh, the battery life is significantly dropping at the earlier temperature zone. From 15 to 70, the most of the battery life is decreased, right? So that's not robust. So we would not like to have a material that quickly drops the battery life when the temperature increases. Then you look at the red one here, A2 material type. battery life is dropping, not as significantly as the black one, but it is still dropping. And then the drop actually accentuates in the second half, from 70 to 125. So again, not very robust. But material A3 uh, is better than those two materials because it keeps the battery life almost constant in the first, from 15 to 70 temperature range, right? 15 to 70 degree Fahrenheit temperature range. It keeps the battery life constant, and then it after that the battery life drops. So it is better than the two materials. So if we have the choice between the three, we would go with material type A3. Also, that leads to some more experimentation. Now we can look at material type A3, and we can do further engineering research to see what modifications or changes can be made in material, so that this second half effect can also be minimized or completely eliminated. So that can lead to more experimentation. Uh, but for now, material type A3 looks the best. So this is where I will stop. As I said, you can manually do these calculations, or you can use any of the statistical software uh, to generate your ANOVA table. And the next thing is you have to look at your residual analysis to see any of the assumptions on residuals are violated. If they are violated, then we will have a problem in our analysis. So I will talk about uh, what happens when we have a case where some of the assumptions on residuals are violated in a future video. So I will stop here. Thank you.